There is actually you've introduced the topic as 1 day for sandstone and 1 day for carbonate, but I think based on the slide that I prepared, we will go for actually a general discussion about these two, especially for sandstone and carbonate stimulation. That is the actually case. So before going to the outline, let me share with you the courses that actually I'm involving with. Well, no, this one is not fully shared. I don't know what is the reason. Is this fully in slide mode? Candidate selection using Excel spreadsheet and also using fuzzy logic system. I've developed several methodologies actually for this one. Specifically, we will go for well test analysis for well stimulation, specifically for matrix acidizing. Also, we have also done several courses using Steamcade for well stimulation, and also the main topic that I'm interested in to share with you is that using manual actually using Excel spreadsheet for design. That means that we don't need actually to have software. So that's why everything will be done by Excel, and you are going to just go through some basics on stoichiometry and also kinetics, and also designing of matrix acidizing. Also, we have a course specific for well stimulation in artificially lifted wells, and also we do some Olga simulation, dynamic simulation for flowback, and then to know what time is the best for flowback, and also what is the type, what is actually the best choke size that we can actually flow back the well. And finally, we have well diagnosis and treatment. This is a general course conducted in the university and industry level. Okay, so this is the outline. The outline, as you can see, we have the introduction consists of history, well stimulation, matrix job, why matrix stimulation engineering. And also, we are going to go for the multidisciplinary nature actually of this area, and then we are going to cover some failures in matrix acidizing, and then we are going for the basics, which are very important: formation type, stoichiometry, acid spending. As you know, we have several actually precipitates that can be actually seen in the majority of acidizing, especially for sandstone acidizing. And then the key factors, we will wrap up this section. And also in the last two topics are matrix stimulation engineering. We are going through the candidate selection, formation damage and diagnosis, and also design, fluid selection, additives, and also the treatment selection for both candidates, for both carbonates and sandstone. And also we are going to have some actually topics about the pumping time, shutting time, the quality control before, during, and after. And finally, we are going to cover a case study. We used, a fine stabilizer together with matrix acidizing in order to actually tackle the clay and other type of. So this is about using this type of actually case study was conducted for artificial lifted well with gravel pack completion. Okay, so this will be the final topic that we will cover in our course here. So one thing that I wanted to emphasize here, that one size doesn't fit all. Okay, so each stimulation treatment should be carefully planned in view of recent experience in the area and also individual well condition. The question is, can we transport any technology from one formation to another and bring in pumps to supply the horsepower? Simply no. We know that each and every one of these rocks and reservoirs is unique and requires different approach based on permeability, formation mineralogy, precipitates, the effect of secondary fractures. So that means we need to customize every fluid, additive, and design to get the most out of the reservoir to achieve economic success. Okay, so this is the okay, so the history, oil and gas operators have used acid treatment, which we call it here acidizing also, to improve well production for almost 120 years. Acidizing predates all other well stimulation techniques, including hydraulic fracturing, which was not developed until the late 1940s. Until the early 1930s, acidizing use was limited by the lack of effective acid corrosion inhibitors to protect the steel tubulars in the well. With the development of effective corrosion inhibitors in 1932, the use and further development of acid treatment of oil and gas wells proliferated, leading to the establishment of well stimulation service industry. Currently, acidizing oil and gas wells is a routine practice for improving productivity. Wells, acidizing is commonly performed on new wells to maximize their initial productivity, and on aging wells to restore productivity and maximize the recovery of energy resources. Okay, so in this slide, we are going to cover some definition of well stimulation. As you can see here, the objective of stimulation is simply, you know, we can actually categorize based on this table that you can see the process flow chart. We can categorize the well stimulation on its application. We apply well stimulation. We can apply well stimulation either in the formation or in the wellbore. Okay, when we are using this in this you know, technique in formation, if the pressure that we apply is more than fracture pressure, so this is called hydraulic fracturing. And in hydraulic fracturing, we have two methods, commonly technologies, which are prop frac, which is using propant, and also acid frac. Okay, acid fracturing. If it's less than fracture pressure, it's called the technology called matrix acidizing. Also, if we use this well stimulation in wellbore, generally inside our wellbore, that means there will be no formation involved. We call it pre-wash, you know, tackling scales, and also like carbonate calcium, you know, or calcite, and also barite, and also organic precipitates such as wax and asphaltene. Okay, so this is, you know, called the using this technique in wellbore. Okay, so we have wellbore clean out and matrix treatment, and also hydraulic fracturing. Okay, so there is another classification. So we call this hydraulic fracturing mechanical stimulation, and also for the matrix acidizing, the name implies is chemical, you know. So that's why, based on the application and based on the you know, characterization, there will be different classification, but this is a general one that we can cover in this workshop. Okay, so what is matrix acidizing? Okay, so matrix acidizing open up new channels in the rock for oil and gas to flow through its. As I said, there will be, you know, based on the all the actually stimulation category, there will be exclusive also that I didn't include it here, but we have also exclusive. We have that conducted before, any other stimulation job. So a chemical treatment injected radially from the wellbore beyond the critical matrix at a pressure below fracture pressure to remove or bypass formation damage. As you can see here in this figure, we have pumping pressure and we have also injection rate. So that means that our pumping rate should be less than fracture pressure. That's why we call it matrix acidizing, and we are not going to create any fracture. But there is a case where we want to actually do some cleaning for the perforation. So that was actually a case that we can increase the pressure to frac the open hole in order to bypass the deformation. Okay, the damage. So matrix acidizing engineering. Okay, matrix success rates range is more than 50%. So return of investment is higher for matrix versus fracturing. And based on the paper that you can see the references in the end of the slides, but based on the paper that is published by Argo company, 25 to 50% of their wells have significant damage. Okay, so there was actually the companies normally reluctant to go for a stimulation. So the main reason that they don't go for it is that they are not aware of the potential benefit. Okay, so what will be the actually increase in production after their well stimulation? So there will be risk and management won't take that risk, and also there will be some operational mistakes. So as you can see here in this in the left table, we have the 4 different columns. We have the area, international, continental US, Alaska, and total. So as you can see, the success rate for matrix stimulation treatment is about 68%. And also the main reason for the failure of matrix acidizing also have been included here: incorrect field procedures, incorrect design, wrong fluid, and also, as you can see here, the majority of the contribution was about the incorrect design, which is very, very important. Some of you may go for a software and use that software, but let me tell you that if you don't know the basics, such as stoichiometry and the kinetics, and also the mineralogy of the formation, there will be a big and a great risk for the failure of your job. That's why, as I told you before, each well has its own characteristics, and also each wells in one field also they have their so this is all about the heterogeneity of the formation that we need to take care of. Okay? So there are several actually multidisciplinary. This is well stimulation is a multidisciplinary nature. That's why there will be several personnel that needs to work together in order to make sure that well stimulation will be successful. So production technology, stimulation is one of the core topics in production technology. And then so the production technologies, of course, is the lead actually for well stimulation. Also, we have well completion. For your information, stimulation is a major expense in many well completion. So we have also geology. It's very, very important. As I said before, we need to know about the geology, about the mineralogy, about the petrology, crystallography, and also mineral resources. So this is having a geologist is a must in the group in order to make sure that actually the success is there, and also the design actually will be based on the minerals that we need to actually dissolve in our. So the production chemistry, whether it's at the surface, tackling and taking care of emulsion, and also doing several lab tests, acid response curve, and also dissolution tests, and other type of topics that are related to lab, and also the production chemistry is very important. So the petrophysicist, we need to know the permeability, we need to know the porosity. That's why it's very important to have different sources of data and different calibration methods. And also for the reservoir engineer, actually, the well test analysis that will be conducted, it's, in order to make sure that the skin is there, and the skin is nothing to do with other actually reasons. So we need to have this data also. For the flow assurance, I'm giving you an example that how flow assurance will help well stimulation, job in order to, so I'm going to show you a slide, and that slide there will be some dynamic simulation showing you the impact of that decision that can contribute to the success of well stimulation. So geomechanics, the variation of temperature, and also the variation of stresses are very important in our case, that the geomechanics also is one area. And finally, the environmental engineering part, that for the flow back, for the injection, for our other, for example, some areas in Middle East still using xylene for tackling asphalting. So xylene is categorized to as one of the volatile compounds, a solvent. So that's why using xylene creates many actually health and environmental hazards. I published one paper about this issue, and that's why this environmental also is very important, that we need to make sure that it's within our regulation. So this example show you the importance of dynamic simulation in the decision. Actually, this is not showing. Okay, so as you can see on the top, we have we have the effect. Here we can see the effect of top choking, and also the effect of orifice. So this is conducted in artificially lifted well. As you can see, if we use actually smaller choke size, the time that we stabilize the production will be about less than 10 hours. Okay, and then if we use smaller orifice size, also we will stabilize the flow back after 20 hours. So that's why this will give you, this is just an example to show you the contribution of the flow assurance engineer for modeling and also for the flow back. As you know, actually the sludge flow and also the flow back is very important. Also the injection part is very important, that we need to actually take care of, and flow assurance engineer is going to actually to help us for the efficient decision making in this regard. Okay, so these are common failure that you can see in well stimulation. Improper candidate selection is damage characterization, so formation damage. So knowing the type of the damage is very important. So we go for a well that is depleted, and we do stimulation. So this is a wrong decision to go for a depleted well. There is some actually, as I told you, some well may have 70% depletion, some wells may have 80%. So that's why the depletion range is needs to be, we need to do nodal analysis in order to make sure that, you know, this depletion will not going to affect the productivity. So the zone coverage, if we have long pay zones and if we have several zones, we need to make sure that the acid will be covered equally in our, you know, for example, the water cut, and also it's very important. Acids, you know, is going to, you know, let me tell you that acid loves water more than oil. So that's why the majority of the acid will go for the water zone. That's why we need to make sure that actually, so independent contact, inadequate contact with damage, and also formation, perforation, fluid incompatibility. So recent sample, lab test, wellbore clean out, rat hole clean out, and also use of incorrect volume of or concentration of the acid, tubing contamination, quality control, bad fluid selection, precipitates of reaction, byproducts, flow back, and fine migration are main reason actually for the failure in well stimulation. So this slide show you. I don't know whether we can, because I see some of you raise his hand. Whether okay. So in this slide, as you can see, we categorize actually the formation type to carbonate and sandstone. As you can see here, the amount of acid needed to dissolve a given amount of mineral is determined by the stoichiometry of the chemical reaction, which describe actually the amount of moles that is required to actually do the. Here in this slide, you can see that the acid that is used for carbonate use HCl, okay, and then this HCl will dissolve carbonate, actually the majority of the carbonate. So knowing the type of formation being acidized and details of its composition, that I mean by mineralogy, is critical to achieve positive results. In carbonate formation, the acid job design is typically based on the use of hydrochloric acid or HCl. And then the objective when acidizing carbonate formation is to dissolve carbonate-based materials to create a new or clean existing pathway or channels that allow the formation fluid to flow more freely into the well. The main readily HCl soluble materials are calcite, dolomite, and siderite, which additionally do not generate any precipitates. Okay, so as you can see, the reaction are included here for the calcite, dolomite, and siderite. Okay, so in sandstone formation, the acid job design is typically based on the use of hydrofluoric acid, or HF, also known as mud acid, in combination with HCl. Sandstone materials are not appreciably soluble in HCl alone, but are much more so in mixture containing HF. So the objective when acidizing sandstone formation is to dissolve fine sand, such as quartz, feldspar, and clay particles that are blocking or restricting flow through pore space, thereby allowing the formation fluid to move more freely into the well. So in sandstone formation, if the sandstone formation contains carbonate materials, then HCl may be added to the treatment. So quartz, clay, feldspar are the main siliceous particles involved in the damage of sandstone. So you can see here, we included some primary chemical reaction in sandstone acidizing. So geological formations are really completely homogeneous. So they contain impurities that can be highly variable in their composition. As a result, designing an effective acid job can be complex. Okay, so that's why most simple acid job design use blend of HCl and HF to respond to the heterogeneous nature of the geological formation. So the strengths of the acid and their volumetric ratio, HCl to HF, are based on the detailed mineralogy of the formation being treated. Okay, so here is that the amount of acid that actually needed to dissolve a given amount of material is determined by the stoichiometry of the chemical reaction, which describe the number of moles of each species involved in the reaction. For example, the acid reaction between hydrochloric acid and calcite can be written as equation number 1, okay, which shows that 2 moles of HCl are required to dissolve 1 mole of calcite. So the numbers 2 and 1 multiplying the species HCl and calcite are the stoichiometric coefficients. When hydrofluoric acid or HF reacts with silicate material, numerous secondary reactions may occur that influence the overall stoichiometry of the reaction. For example, when HF reacts with quartz or SiO2, the primary reaction, which is reaction number 2 here, producing silicon tetrafluoride or SiF4 and water. So the stoichiometry of this reaction shows that 4 moles of HF are needed to consume 1 mole of SiO2, okay, or quartz. However, the SiF4 produced may also react with the HF to form fluorosilicic acid, okay? So according to equation number 3. So here, if the secondary reaction goes to completion, 6 moles of HF rather than 4 will be consumed to dissolve 1 mole of quartz. A complication is that the silicates may exist in various forms, so that the total amount of HF required to dissolve a given amount of quartz depend on the solution concentration. Okay, so that's why also when we actually do a stoichiometric analysis, so we can also determine the acid, that is the amount of acid, the concentration of the acid, and also we can determine the porosity that is increased in our actually critical matrix zone. Okay, so that's why normally the typical acid volume range between 10 and 500 gallon per foot, while a volume of 500 gallon per foot may appear to be a large in matrix acid job, assuming that we have about 25% porosity. The acid would be displaced less than 20 feet from the wellbore. Okay, so this is showing you, as you can see here in this figure, we have the rock that is contains some pore filling clay, such as kaolinite, and also some illite, and also some cement, such as carbonate. So that's why in totality we have different mineralogies. So that's why in this case we use HF. Okay, normally the concentration of HF and HCl for primary precipitates, we can categorize it to do before and after. So for the primary, we have 12% of HCl and 3%. So after we actually finished our primary, the HCl will reduce to 10% and the HF will be reduced to 0.1%. So aluminum, ALF, and also silicates will be some precipitates of the byproduct of this actually reaction. And when it goes to the secondary one, acid will be reduced to 4%, the HCl, and HF will be same, but we have high aluminum fluoride, and also we don't have any silicon in the secondary one. And when it goes to the tertiary, then both HCl and HF have been spent, and we have high high aluminum also fluoride actually precipitates. So that's why what we can do in this case is that in our course for the using actually stoichiometry and kinetics, we will use this basics in order to actually design and have our HCl pre-flush. Also, we will do some acid mineral reaction kinetics, and also we will do some, we will know about the dissolution rate and also the relative reaction rate of the minerals. Actually, one of the main thing that we can get from the basics of this stoichiometry is that how we can know the effect of these precipitates on our well productivity. So if we have a well, for example, with drainage radius, and also we remove the damage, and then we left with about 1 cubic feet of cubic feet per feet of the reservoir thickness of spent acid. So this will create some precipitate that reduce the permeability, for example, to 5 to 10% of the original permeability. So we can go for a design of an overflush, and that this overflush can actually push this precipitates far away from the wellbore and displace also displace it farther into the formation from the critical matrix actually area. So that's why by using these basics, we can determine how the productivity of the well is influenced by the location of the zone of these precipitates. Okay, so two key actually factors dominate the treatment selection and design. Actually, the process is the formation type, whether it's carbonate, sandstone, or shale, and also the having this formation permeability. Of course, knowing the type of the formation will force us to come up with a specific acid type. Regarding the permeability, permeability will help us to come up with the pumping pressure. There is an equation, and from that equation, we can come up with the pumping pressure that is required actually to, and also there are another factor, which is temperature. So this temperature will force us to actually select the additive, other organic actually acids, and other types of acids such as chelate and newly developed acid that can work for temperatures, high temperature wells. Okay, so in this case, formation permeability, as I said, determines the pumping pressure required to place the acid into the formation. In general, the lower the permeability, the higher the pumping pressure. In high permeability formation, the acid can be pumped into the matrix of the formation as relatively low pumping pressure. As said earlier, if the pumping pressure is below the formation fracture pressure, the treatment is called matrix acidizing. However, in lower permeability formation, the acid cannot be pumped into the formation matrix as readily, but is pumped through existing or induced fracture at higher pumping pressure. So if the pumping pressure is above the fracture pressure, so the treatment is called fracture acidizing. Of course, if you use this in carbonate. So there is no actually, there is not an absolute value for formation permeability that separate matrix and fracture acidizing. However, the range of values where this may typically occur between 0.1 millidarcy and 10 millidarcies, depending on the case specific situation. Okay, so this is about matrix stimulation engineering. So engineering is about practical application of scientific and mathematical practices. So the proper engineering of matrix treatment includes many tasks. and a structure methodology. Each is important and should be accomplished based on the best available data and knowledge at hand. So the proper engineering of the matrix treatment includes, as I said, many tasks. So the design engineer rarely has all of the required data information, but this does not mean that the treatment will be unsuccessful. So as you can see here in this chart, this process also can be modified, but this is based on actually the available literature and also experience from the field. So candidate selection, then we go for damage characterization, and then we go for the treatment selection. For example, if the damage is fine, and if we know what is the type of the clay that is available there. For example, if there is chloride, so we know that iron is included in chloride. So that's why there are several actually procedures in order to come up with the treatment selection. And then based on the treatment, we will go for the fluid selection, and then based on the permeability and also the job that we are going to conduct, we will going for the pumping schedule. However, if we have conducted any injectivity, that is our pre-treatment, we can modify and adjust our pumping pressure, and this is specifically conducted for hydraulic fracturing. And then we will execute the job, and then after that we will do we'll go for the post-treatment. Some of the job may not give actually give you you need to wait actually for several days or weeks in order to come up with. But there are several tests and several monitoring techniques that you can use in order to actually check the successfulness of the job. For example, in the case of fine migration, we need to do some surface tests, sand count, and also some XRD and other shakeout in order to come up with this fact that the fine is produced or not, or if the fine and if the sand is produced, So that's why I'm not going to go for the details, but this is somehow the process of matrix stimulation engineering that we need to go through. Okay, so this is showing this table, showing you the main parameters that can be used for candidate selection. So the selection of the stimulation candidates that potentially meet the economic screening criteria is the key to a successful stimulation campaign. So this involves several stages, such as identification and quantification. But in this system, as you can see, summarizes typical values for the minimum requirement for a successful stimulation treatment. So the criteria, as you can see, we have saturation, we have water cut, we have reservoir height, and one of the most important topic that you need to consider is that when the reservoir is high enough, you need to use diversion, diverters, and there are several diverters, chemical and physical, and also foam and other type of diverters that depends on the actually the fluid and the formation characteristics. So if we go for the permeability, which is the next one, if we go for matrix acidizing for the gas reservoir or the oil reservoir, so this is all about for the gas, it should be about more than 1 millidarc, and for the oil it should be more than 10 millidarc. As I said, this is not these not fixed numbers, and the specific characteristics of a well needs to be considered also. So the skin normally should be more than 2, but for the carbonates, of course, we can You can also do stimulation for zero skin or positive skins also, but this is not applies for sandstone acidizing. For reservoir pressure, for the gas reservoir, it should be about 1.5 to 2 times of for the abandonment pressure, and for the oil, it should be about 70% of the depletion. And we need to make sure that the production system can handle the increased production of the. So that's why. There are so many actually other variables that we can actually go through one by one. As I said, we can do it conventional. We can do conventional analysis, such as using this equation, steady state equation, and coming up with doing some sensitivity and nodal analysis in order to make sure that everything in order and works well. We can, know the oil-water segregation through PLT, reservoir saturation tool, and as I said, acid normally will proportionately acidize the water zone. So skin also needed to be soluble in acid. It's very important to make sure that we are not using acid for organic materials such as wax or asphaltene. So that's why these are some general criteria that we normally use for matrix acidizing. For more references, these are some references that included in the end of the presentation. So formation damage is one of the topic that we need to go through, and this is one of the main actually stage gates that we need to go through. That's why in this case, as you can see here for this slide, partial or completion plugging of the near wellbore area, which reduces the original permeability of the formation. Damage is quantified by skin. Change in damage skin factor. So we can do matrix acidizing. So this matrix acidizing can be conducted in sandstone reservoir. So skin at the best reduced to 0. For the carbonate, however, can generate a negative skin. So for the fracturing, this is, a negative skin is possible. Of course, the fracture length is very important for our case. So this table, showing you the type of the formation damage. So it's classified. So this is a classification. Actually, we have natural damage and induced damage. For the natural damage, we have fine, we have swelling clays, we have organic deposits such as paraffin, asphaltene, and wax. We have water-formed scales such as calcite, carbonate, ferrite, and others. We have also emulsion that will be created based on the mixture of the oil and water. And also the second category is the induced damage, which is plugging by entrained particles, wettability changes, acid reaction, and also water blockage, and also bacteria are some of the this is, of course, if we have the electrical logs, we can come up. This is the only way that we can actually make sure that the area of the damage is located. Where is the location of that area? Production and injection records are very important. Comparison of production performance of offset wells, pressure transient well test analysis, production records. Laboratory test is very important. make sure that you do actually laboratory tests for the cores in order to come up with the acid response curve, and also determine exactly the mineralogy of your core in order to design an effective actually acid and also production records, radial flow equation that I showed you before, field production history, mechanical condition of the well, and also previous stimulation treatments. And these are some actually techniques that can be used for diagnosis of formation damage. So this table also show you the different type of damage, starting from fine, swelling clay, asphaltene, paraffin, emulsion, wettability, and also water blockage and scale deposition. In the next column, the diagnosis and also the treatment are included in this table, and you can go through this table and actually know that there are so many differences in to tackle each of these type of damage inside our well. Okay, so this is actually the recommendation from MacLeod for sandstone acidizing. So as you can see in the first column, we have the formation, and we have the main acid, and we have the pre-flush at the last column. If the solubility of the test is more than 20%, so we need to make sure that we use HCl only. Okay. So if the permeability is more than 100 millidarcy, and after that we need to go for the mineralogy of the formation. So this is all about the percentage of the quartz, feldspar, clay, and iron. Okay. So also for the iron, if we have chloride clay, so that's why different percentage of HCl and HF are required in order to tackle those issues. Also, the pre-flush is very important here in our case, and we need to make sure that we adhere to the recommendation. But as I said before, each well has its own characteristics, and also based on the mineralogy, and that is conveying the heterogeneity of the reservoir, we need to do actually a specific lab and formation damage characteristics, formation damage diagnosis in order to come up with the specific damage. Regarding the low permeability rocks, if it's less than 10 millidarcy or 10 millidarcy, so if we have low clay content, less than 5%, we can go for 6% HCl and 1.5% HF, and also for the high chloride. That's why, as I said, this chloride is very important for designing actually the acid volume and the concentration. In addition to the chloride, halite and monzonite, and also the kaolinite, and some of the swelling clays are also important in order to one of the mistakes that the majority of the operator also do is that they tackle the cementation of the sandstone rock. So that's why after the acidizing, there will be high actually fine and sand production in that well. That's why you need to make sure that the type of the cements, you are not going to tackle that cements in your rock. That's why you will be inducing some other issues and problems such as fine and sand production in your well. There are so many cases that are documented in the literature and papers about this topic. So this table show you actually the damage type, and if we are going for actually carbonate stimulation, for this case, we can see that we have if we have walk and fractures, and if we have for example, if we are going to tackle the perforation, that's why we need to come up with we need to select acid wash and also matrix treatment. If the damage is shallow, we need to use matrix acidizing. If the damage in shallow and it contains some fractures, we need to also use matrix treatment. If we have deep damage without any fracture, so we use matrix acidizing. If the damage is deep and also we have fracture and wart, we need to use closed fracture acidizing technique. And for low permeability without fracture, we need to use massive hydraulic fracturing and acid fracturing. So for your information, actually, the closed fracture acidizing is a technique that is designed to overcome inadequate conductivity development in traditional acid fracturing treatment. However, achieving adequate fracture lengths is challenging due to the fact that acid spending rate and also the high corrosion rate of the well tubulars, specifically at high temperature. Okay, so it's important to know a specific material that is damaging the formation around the wellbore. So selection of the chemical for any particular application will depend on which contaminants are plugging formation permeability. HCl will not dissolve pipe dough, paraffin, or asphalt. Treatment of these solids or plugging agents requires an effective organic solvent, usually an aromatic solvent such as toluene or ortho-nitrotoluene. So acetic acid effectively dissolves calcium carbonate scale. However, it will not dissolve ferric oxide, or we call it iron oxide scale. HCl dissolves calcium carbonate scale quite easily, but has little effect on calcium sulfate scale. Calcium sulfate can be converted to calcium carbonate or calcium hydroxide by treatment with potassium hydroxide or sodium carbonate. So HCl can be used to dissolve the converted scale. So calcium sulfate also can be dissolved in one step with sodium salt or of ethylene diamine tetraacetic acid or ADTA. So HCl will not dissolve formation clay minerals or drilling mud. That's why we use HF to dissolve these aluminosilicates in rock pores around the wellbore. So because different plugging solids require different solvents for their removal, there is no universal solvent for wellbore damage. So treatment based on such a premise often will yield to disappointing results. So this is showing you actually the steps that normally will be conducted in acidizing. As you can see, we have a pre-acid pre-flush, and then we will go for the next, which is the pre-flush, acid pre-flush, and then we will go for the main treatment fluid. So this is, and then we will go for our overflush. So we will push the acid into the formation, and after that, so as you can see, we have pre-flush, acid, pre-flush, and also main treating fluid, and also overflush. And finally, we have diverter stage, and all these steps can be actually repeated again if we are going to do stimulation in a thick reservoir. Okay, so these are some additives that using, this slide present the major groups of acidizing additives that are available. So each of these groups, along with their mechanisms and importance, will be covered separately. So we have inhibitor, surfactant, neutral solvents, iron control, friction reducers, clay control, and specialty additives that are used for. So inorganic corrosion inhibitors are, are no longer an option, as they are extremely toxic and pose a great danger to the environment. So organic corrosion inhibitors have been proposed as an alternative since 1970s. However, organic compounds still pose a hazard in their use. Natural extract as alternative have been proposed in their inhibition ability. That's why, the use of, for example, we use henna, extract and some aqueous garlic pear extract as corrosion inhibitor that shows some very good, actually positive results with lower corrosion rate compared to some conventional inhibitors. Okay, so this is about pre-flush. That's why chemical or mechanical, cleaning of the tubing and casing. So well-bore cleanup is a must before every matrix treatment. So this is actually normally to prevent the injection of iron compounds, rust, and other deposits into the perforation and formation during the main treatment. As you know, the availability of iron can cause creation of slug, and also can trigger other precipitates. Okay, so using this cleanup stage, we need to make sure that we will have a flowback after doing, after doing our clean out, and also we need to jet our perforation. So that's why this is an important step in our acidizing. Okay, so let's see the type of. Okay, so I think do we have time to continue? Recommend for pumping time. Actually, that we need to consider. So okay, the pumping time, actually for this, the time is determined by the type of acid used and also by the downhole factors such as formation type, bottom hole temperature, and bottom hole pressure. So after an acid solution has been neutralized by reaction with the formation, it is no longer stimulation fluid. However, it may become harmful to the formation permeability if allowed to remain downhole. So in general, if we use, hydrochloric acid with limestone, we need to have about 2 to 4 hours pumping time in a vertical well. If it's going for the horizontal, it takes more than 6 hours. So it depends on the treatment volume, what is the size of the formation, the pumping rate, is there any equipment limitation, and also the frac gradient or let's say the well integrity, and also the well temperature, which is depends on the governs our corrosion effectiveness, and also for the fluid rheology and friction pressure. Okay, for the shutting time, actually the shutting time is the length of time a well is closed in after stimulation treatment is completed. So, of course, before the flowback is initiated. So this time is determined, as I said, by the acid use and other information. So we have mineralogy, bottom hole temperature, and also the the live acid versus spent acid. After a time, you know, depends on the acid type, the acid will be spent. So the shutting time for HCl is 0. The recommendation is that you flow back as soon as possible. For the retarded acid, we have, you know, the time is included here, about 2 hours. For the organic one, we can have also about 1 to 2 hours shutting time. And if we are using HCl, you know, and HF, also the time included, the shutting time is included here. So these numbers are that are included here depends on the type of the, as I said, type of the formation, the temperature, the pressure, and also the results of mineralogy and other laboratory tests that is determined there. And also we need to make sure that the precipitates are not going to be to happen for our case when we actually inject our acid. So the shutting time depends on these variables. So what are the quality control before pumping? We need to make sure that all additives are available. We need to do circulation of the acid in storage tanks. We need to make sure about the concentration of the acid. That's why we need to have a titration kit in order to make sure that the acid concentration is correct. We need to take sample of the acid and also fluid to be pumped for the later analysis if needed. We need to collect also samples. We need to know the mass. Maximum anticipated surface pressure is very important based on the fracture pressure. We need to make sure that we are not going to actually pass this pressure. Also, we need to monitor the pressure time recorder for the proper operation. Okay, so there are also quality control during pumping. We need to watch the pressure response when acid reaches the formation. If the formation is sandstone, the surface pressure should slowly decrease if the rate is held constant. If the surface pressure rises sharply or rises continuously for several bars of acid, the acid may not be removing the damage or may be damaging the formation. So acid injection should be stopped and the well flowed back immediately. So samples of the flowback acid and solids should be sent to the service company for laboratory analysis. So if the formation is limestone, so the pressure may drop rapidly and diverting stage may be needed. Okay, so if we are dealing with the limestone. So if the treatment is an acid frac on limestone or dolomite, so the pressure may be stable or decline slowly after breakdown. A rapid drop in pressure may indicate need for fluid loss or diverting agent. So the quality control after pumping. Okay, do not shut in the well after acid injection. Flow the well back to tank or pit as soon as the flow line is connected. Collect at least 3 1/4 samples of backflowed acid for analysis. Sample the acid backflow at the beginning, middle, and near end of the flow. So if on swab, get the sample from every other swab run. Secure a lab analysis for the amount, size, and type of solids, and also strength of the return acid. We need to make sure that what will be the strength of the acid. So this will determine actually the reaction. Also the total of the acid, the iron content. So we need to see what is the ppm value of the acid. That's why we need to know actually the amount of iron before and after. And after we need to have 3 samples also in order to make sure that everything is in order. And okay. And also we need to have the report and the pressure chart to the office for evaluation and placement into the well life. And these are some references that included for your information actually. In this case, as you can see, the majority of the references here. So that's why I think I'm going to show you some case study of a field actually pilot of fine migration matrix acidizing. That's why I think we are going to go through this case study in tomorrow's session. Okay, thank you very much.